Hello again, everybody, and welcome back. Today we're in section 3.4 of statistics, and we're going to be talking about measures of position and outliers. I'm going to show you how to calculate and interpret z-scores, how to interpret percentiles, how to find and interpret quartiles, also how to find and interpret the interquartile range, or IQR, and we'll talk about how to find outliers for a data set. So here we go. First up, let's talk about the z-score. A z-score is just a number that tells us how many standard deviations a value is from the mean of a population or the mean of a sample. So here we have two different formulas for z-score. Functionally, they're the same. Let's take a look at the population formula, and then we'll look at the sample formula. The population z-score formula says z equals x minus mu, and remember mu is the population mean, divided by sigma, and remember sigma is the population standard deviation. It's important to note the way this is written, we have to do the subtraction first and then divide that difference by sigma. So you can see that if you have a data value and you subtract mu from that data value, you would now know the difference between x and mu. Then to find out how many standard deviations that difference represents, you just divide by the standard deviation. And likewise with the sample z-score formula, we have x minus x bar divided by s. And remember, x bar is the sample mean and s is the sample standard deviation. And note here again, we have to do the subtraction first, and then we divide the difference by s. Now both of these formulas do the same thing. It's just that the population formula uses parameters mu and sigma, and the sample formula uses statistics x bar and s. Now note that the z-score is a unitless number. Our data will have to be measured in some unit, say miles or inches or feet or gallons. Our data has to be measured in some unit. However, no matter what units our data is measured in, when we calculate the z-score, x minus mu will have whatever unit of measure, and then when we divide by the standard deviation, it has the same unit of measure. Therefore, we'll have unit divided by unit, and the units will cancel out. So the z-score has no units. And another important thing to know about z-scores is that the distribution of z-scores for a particular data set always has a mean of 0 and a standard deviation of 1. This will become much more important later in the course, but it's also good to know right now. The distribution of z-scores has a mean of 0 and a standard deviation of 1, and it just makes sense that the mean should be 0, because if you think about it, this top part of the formula is just a deviation. And if you remember, we talked about in section 3.2 when we first learned about standard deviation, that the deviations for a data set always have to add up to 0. Well, if you add all the deviations together and get 0, and then you divide by the number of observations, of course the mean of the z-scores is going to be 0. That just makes sense. And again, the standard deviation is 1. Also note that z-scores are always rounded to 2 decimal places. Always. There are no exceptions to this. We always round z-scores to 2 decimal places, and that's because of the table that I'm going to show you when we get to chapter 7. Here are our formulas again, and I just want you to notice a couple more things about these formulas. First of all, if we have a positive z-score, it means that the data value we plugged into the formula is greater than the mean. You think about it, if you plug in a number here that's larger than mu, then x minus mu is going to come out positive, and so the z-score would be positive. On the other hand, a negative z-score means the data value is less than the mean, because if you put a number here that's less than mu, then x minus mu will come out negative. And finally, if the data value is equal to the mean, the z-score will be 0. So think about plugging in a number here that's equal to mu. Then mu minus mu would give you 0 for the top, and 0 divided by whatever the standard deviation is would give you 0 as a z-score. Now, because the z-score standardizes the data, it allows us to compare data that's on different scales. So let's look at this example. This says, determine whether the New York Yankees or the Cincinnati Reds had a relatively better run-producing season. The Yankees scored 859 runs, and they play in the American League, where the mean number of runs scored was mu equals 721.2, and the standard deviation was sigma equals 93.5 runs. The Reds scored 790 runs, and they play in the National League, where the mean number of runs scored was mu equals 700.7, and the standard deviation was sigma equals 58.4 runs. Now note that it's not really valid for us to just compare the Yankees' 859 runs to the Reds' 790 runs, because they don't play in the same league. The American League allows a designated hitter, so the mean number of runs scored in the American League is actually a little higher than the mean number of runs scored in the National League. So it's not really fair to compare the Yankees to the Reds based on raw numbers. But what we can do is convert the number of runs scored by each team to a z-score, and that will level the playing field for us. So let's start with the Yankees. The American League, where the Yankees play, had a mean of 721.2 and a standard deviation of 93.5. If we plug 859 into our z-score formula, we'll have 859 minus 721.2 all divided by 93.5, and that's going to come out 1.47. On the other hand, if we do the same thing for the Reds, the National League, where the Reds play, had a mean of 700.7 and a standard deviation of 58.4, and again plugging into the z-score formula, we get 790 minus 700.7 all divided by 58.4, so the z-score for the Reds is 1.53. Now what this tells us is that the Yankees' number of home runs is 1.47 standard deviations above the mean, and the Reds' number of home runs is actually 1.53 standard deviations above the mean for their league. So it turns out that the Reds had a little better season than the Yankees. Now before we leave this example, I want to show you a couple of mistakes that I see people making when they show their work with the z-score formula. First of all, I see people trying to do this, and I think it's because when you type your work in MyLabs Plus, if you want to format your work as a fraction, you have to use that math expression tool, and sometimes people just don't want to do that, and so they'll try to type everything on one line. Well, the problem here is that order of operations gets in the way. Remember, order of operations says that division takes precedence over subtraction. So this actually does not say do the subtraction first and then the division. It actually says do the division first. So the way this is written, you'd have to do this part of the calculation first, and 859 minus this quotient actually gives you 851.29 and not the z-score you were looking for. And here's another thing that I see people doing. They'll try to break the calculation into two steps. They'll say 859 minus 721.2 is 137.8, and then they'll tack on this divided by 93.5. And I think what they're trying to do is escape the problem that they see here. But the problem with this is it's just not true. This says that 859 minus 721.2 equals 137.8 divided by 93.5. It doesn't. It just equals 137.8. And I know what they're thinking is that you get the 137.8 and then you divide by 93.5. And that is what they're thinking, but that's not what's written here. What's written here says that this subtraction equals this quotient, and it does not. And a lot of times they'll even go on to put the answer after it. If you read this from left to right, it says that this subtraction equals this quotient, which equals 1.47. In other words, what this says is that 859 minus 721.2 equals 1.47, and it's not true. So how should you show your work? Well, I want you to do it the way I did it on the last slide, so it should look something like this. Z equals x minus mu all over sigma, and then you can just give the z-score rounded to 2 decimal places. And this is how you show your work when you calculate a z-score. Now let's leave z-scores for a few minutes and let's go ahead and talk about percentiles. Just as a median divides the data into 2 segments, percentiles divide the data into 100 segments. I know you've seen test results and things that say like the 98th percentile or the 63rd percentile. So the kth percentile of a set of data, which we write as P sub k, is a value such that k% of the observations are less than or equal to the value. For example, P sub 30 divides the lower 30% of the data from the upper 70%. So let's take a look at this diagram. This number line is supposed to represent our entire data set. So here's the smallest data value right here and the largest data value up here. And you can imagine little boundaries that divide the data into 100 little sections. So this represents P sub 2, and this is the number that divides the bottom 2% of the data from the upper 98%. And this is P sub 99. In other words, the 99th percentile divides the lower 99% of the data from the top 1%. So to say that someone's test score is in the 99th percentile is to say that that test score is greater than or equal to 99% of the total scores. So let's look at example 2. This says Jennifer just received the results of her SAT exam. Her SAT mathematics score of 600 is in the 74th percentile. What does this mean? Well, it just means that Jennifer did better than or equal to 74% of those who took the test. Now let's move on from percentiles and talk a little bit about quartiles. The most common percentiles are actually the quartiles. Quartiles divide the data into fourths, or 4 equal parts. So here's that little number line again. And notice here we have the lower 25% of the data, and here's Q1. In other words, Q1 marks off the bottom fourth from the top 3/4. And therefore the first quartile is the same as the 25th percentile. And then notice that we have 25% more of the data, and then we encounter Q2. So Q2 divides the lower 50% of the data from the upper 50%. And therefore the second quartile is the same as the 50th percentile, and these are both the same as what we've already been referring to as the median. And now the third quartile divides the lower 75% of the data from the upper 25%. So the third quartile is equivalent to the 75th percentile. Notice that the middle 50% of the data would have to be between Q1 and Q3. Now let me show you how to find the quartiles. It's very closely related to the method we used for finding medians. To find the quartiles, we arrange the data in ascending order, and then we determine the median or second quartile, known as Q2, and that's going to divide the data set into halves, the observations below the median and the observations above the median. The first quartile is the median of the bottom half, and the third quartile will be the median of the top half. Now I imagine that one question you have is, okay, so after we find the median, then does the median itself count in the lower half or the upper half, or does it not count at all? And the answer is, different books approach that question different ways, but our book says no, we do not include the median when we find the quartiles. So I'll show you in a couple of examples what we're looking at. So this says find the quartiles of the data set below, and if you count these, there are 13 values here, and that's an odd number. So to find the median, we'll say 13 plus 1 is 14, and 14 over 2 is 7. That means the median of this data set is in the 7th position. So 1, 2, 3, 4, 5, 6, 7. This 8 is the median. And that divides the data into two sections for us, a lower half and an upper half. When we find Q1 and Q3, we'll leave this 8 out of consideration entirely. So now we're going to find the median of the lower half, and that's going to be the average of these two middle values. So the average of 6 and 6, of course, is 6, and so Q1 is 6, and it falls in between these two 6s. And the median of the upper half is going to be the average of 12 and 15, which is 13 and a half. So now notice that there are 3 values to the left of Q1. There are 3 values between Q1 and Q2. There are 3 values between Q2 and Q3, and 3 values above Q3. And since there are 13 values total, 25% of 13 is about 3, and so we have 25% of the data here, 25% here, 25 here, and 25 here. And notice that the middle 50% of the numbers falls between Q1 and Q3. Now let's do the same thing for this data set. There are 12 values here. So to find the median of this data set, we will average the two middle values. And the average of 2 and 3 is 2.5. Now, since the median is 2.5, neither the 2 nor the 3 has been used up, so to speak. So we will include the 2 in the lower half of the data, and we will include the 3 in the upper half. And so now we have 6 numbers in the lower half, so Q1 will be the average of these two numbers, which is 1.5, and Q3 will be the average of these two numbers, which is 6. So now again, notice there are 3 numbers that are to the left of Q1, 3 numbers between Q1 and Q2, 3 between Q2 and Q3, and 3 that are above Q3. In other words, Q1 divides the lower 25% of the data from the upper 75%, Q2 divides the lower 50% from the upper 50%, and Q3 divides the upper 25% from the lower 75%, and the middle 50% of the numbers can be found between Q1 and Q3. And now I'd like to make sure that you know how to find the quartiles on the graphing calculator. The larger a data set is, the more tedious it becomes to try to find the quartiles yourself. And it's so easy to make a mistake, especially with a large data set. So we want to let the calculator do the job of moving the numbers around for us. Here we have a data set of 18 numbers, and some of these numbers are pretty large. So I just want to show you that I've already entered these numbers into list 1. You can see them here in list 1. And now to get the calculator to find the quartiles for me, it's the same process that we used to get the calculator to find the mean and the standard deviation. So all you have to do is press Stat, Calc, one variable Stats, and now I'm on the old operating system. If you have the new operating system, make sure and tell it that your data is in list 1 or whatever list you used, and leave the frequency list blank. But I am just going to now press Enter because I do have my data in list 1, and if I don't tell it which list to use, it will assume I want to use list 1. So I'm going to press Enter, and here we have this screen that we've seen so many times before, and let's scroll down, and here we have the second screen of statistics, and notice that it gives us the minimum and the maximum in our data set. And notice that here we have the median, which we also know as Q2. So we have here Q1, Q2, and Q3. So Q1 is 735, Q2 is 1805, and Q3 is 4668. Now, since quartiles don't change with extreme values, they are resistant. Remember, we've talked about resistant statistics before. In section 3.2, we saw 2 measures of dispersion that were not resistant. We talked about range, And remember, range is only calculated using the most extreme values, the largest value minus the smallest value. So definitely range is not resistant to extreme values. And we also said that standard deviation is not resistant, because remember, standard deviation is calculated using the mean. And we know from section 3.1 that the mean is not resistant. Therefore, standard deviation is not resistant either. But there is another measure of dispersion that is based on quartiles that is resistant, and that is the interquartile range, which we usually see abbreviated IQR. And the interquartile range is the range of the middle 50% of the observations in the data set. In other words, IQR is the difference between Q3 and Q1. IQR equals Q3 minus Q1. In the same way that range is largest value minus smallest value, interquartile range is largest quartile minus smallest quartile. The more spread a set of data has, the larger its IQR will be. Now let's take the quartiles that we found in example 4 using the calculator, and let's find the interquartile range. IQR is something that the calculator won't do for you automatically, but it does give you the quartiles, and so after that all you've got to do is subtract. So IQR is equal to Q3 minus Q1, which is going to be 4,668 minus 735, and when we subtract there, we find IQR is 3,933. Notice that even if a data set contains extreme values, the quartiles won't change. Therefore, for skewed data, the best measure of center is median, as we said in section 3.1, and the best measure of dispersion is IQR. Both of these are resistant, so they are better to use with skewed data. For symmetric data, the best measure of center is mean, and the best measure of dispersion is standard deviation. So you'll frequently see median and IQR reported together for skewed data, and you'll frequently see mean and standard deviation reported together for symmetric or bell-shaped data. Now, observations that are very extreme are referred to as outliers. To determine which values are outliers, we'll calculate two numbers that are called fences. Any number that's not between the fences will be considered an outlier. The formula for lower fence is Q1 minus 1.5 times the IQR. And the formula for upper fence is Q3 plus 1.5 times the IQR. So if we take Q1 and subtract something from it, that's going to move the lower fence to the left of Q1. And then if we take Q3 and add something to it, that's going to move the upper fence to the right of Q3. So the fences are really a little more spread out than the quartiles, and any number that's not between the fences is considered an outlier. Now you might say, well, where did the 1.5 come from? Somebody asked the man who came up with this formula, somebody asked him once, how did you choose 1.5? Is it based on some mathematical truth or something? And he said, no, I didn't think 1 was big enough and I thought 2 was too big, so I settled on 1.5. This is purely a man-made value, and somebody else in a different time and place might have defined the fences differently, but this is what statistics has been using for years now. So let's take our data that we used in example 4 that we already have the quartiles for, and we've already found the interquartile range, and let's calculate the fences and see if this data contains any outliers. So for the lower fence, we know that's Q1 minus 1.5 times the IQR, so I'll just plug those numbers in. 735 minus 1.5 times 3,933, and that's going to equal negative 5,164.5. And then the upper fence is going to be Q3 plus 1.5 times the IQR, so that's going to be 4,668 plus 1.5 times 3,933. and that gives us an upper fence of 10,567.5. Now let me just draw you a little picture here. If I have this line segment spread out so that the minimum value is at the left end of the line and the maximum value is at the right end of the line. Well, I remember from our previous example that Q2 was 1,805, so let me just put that here. And I can see that Q1 is 735, so that's going to go somewhere in here. And Q3 is 4,668, so let me put that up here somewhere. And now keep in mind that 25% of the data are larger than Q3, 25% of the data are smaller than Q1, and 50% of the data are between Q1 and Q3. Now, the outliers are any numbers that lie outside the fences. So let's see if we can put the lower fence on our number line. Well, the lower fence is negative 5,164.5. So that's way smaller than the smallest value in our data set. So we don't have to worry about any values that are outside the lower fence. But the upper fence is 10,567.5, which is going to go about here. And any numbers that are outside the upper fence are also considered outliers. And I know we have at least one. We have 21,147 as our largest value. That's clearly outside the fence. But any numbers that are outside the upper fence are considered outliers. Now, let me give you just a hint here. If you perform this analysis and you find that 5 or 6 numbers are outliers, then you've done something wrong, because by definition, outliers are far away from the rest of the data, and there should only be a couple of them, 2 or 3 maybe. If you have 10 outliers on a small data set like this, well, something's wrong. They can't all be far away from each other. So now our job is to look through this data set and see if we see any other numbers besides this 21,147 that are outside the upper fence. So I'm looking for anything bigger than 10,567. And I see a 10,000 there, but that 10,034 is just inside the upper fence. And I don't really see any other values that are outside the upper fence except the one we already had, which is that 21,147. So our only outlier is that 21,147.